This talk is going to be partly historical, so let me open with a couple of ideas, major ideas in the history of mathematics. So certainly one major idea was the idea of a group which clearly belongs to the 19th century, from its first inception to its development, and by the end of the 19th century, I think it's fair to say that most of the groups we know today had been explored. Another one is the idea of homology, which is clearly an idea of the 20th century, although it has precursors in the 19th century. And it's by now, well, there's a random list of types of homology that have been developed as the century has gone on. There are many more. I think you can say that it's entered almost every field of mathematics. So I wonder if anyone here is brave enough to speculate if there are ideas of this level out there which are going to similarly grow in the 21st century.
Quantum field theory.
Right. Good. We have a brave person. Yeah, I think that's a. In fact, you could almost say that it's entered many fields of mathematics even now.
Just waiting for the definition, like those things.
Yeah. In some sense, it's a different situation because it's not clear why all the appearances of the word quantum in mathematics are parallel to each other. But anyhow, about bravery of speculation, most people would say, well, let's let history see. But Poincaré was brave enough. Topology as a subject began clearly with a series of papers of Poincaré, which are 100 years old. There were precursors in some conversations between Riemann and Betti, and the idea of homology sort of came out of those. But after Poincaré's papers, then you can just see it mushrooms immediately. Great debates. Many people start turning to it as their main field of study. Poincaré in this original paper had the insight to say that the reason for studying topology was that it will be applicable in many different areas of mathematics. So he said in his beautiful introduction that he would restrict himself to only mentioning three, and the three he mentioned were algebraic geometry, which is really goes back to Riemann, analysis ODEs, actually in his case, in the case of his problem, and group theory. But he made it clear that from his perspective, these were only three of the many possibilities. In my own view, this is, well, I'm more attached to this, to Poincaré's paper as an introduction to the, to what was going to come than I am to Hilbert's famous list of problems. Well, anyhow, this is a way to go in by the back door to my main topic, that from the very beginning, topology was supposed to be an applied subject. Poincaré made it clear that it was worth spending this amount of time on it because of its potential applications.
Applications to mathematics.
Yes, all of Poincaré's applications were applications to mathematics, and I should make it clear that's what I mean in my title, although certainly topology has been applied outside of mathematics as well. Speculating about applications, I drew a historical graph, which, I mean, the dedication to applications both inside and outside of mathematics has not been uniform throughout the century, it seems to me. It sort of was high at the beginning, high at the end, and somewhat lower in the middle. I think this is true when you look at mathematics as a whole. Well, I've given some examples. And certainly many of the people of Bourbaki are now writing these retrospective treatises explaining why at this time it was very important to consolidate the foundations of mathematics. And I think it's also true in topology, and that's the main subject I want to speak about. In the beginning, of course, Poincaré said it was applied, and it was very applied in the early days. It was the main people who studied it were people who were also interested in applications. However, already in 1940, in the 30s, I guess in 1935 there was this enormous topology conference with only topologists present. Already in the 30s, it was sort of drifting off into its own world. An interesting historical remark is in the late 30s, characteristic classes were being developed. So Todd was finding these beautiful cycles on algebraic varieties, and Whitney, Stiefel, and Pontryagin were finding these beautiful cycles on topological spaces. There's no evidence reading either side that they had the idea that they might be related. Of course, I mean, it was at least a 10-year period that both groups were doing the same thing before, as so far as one can tell from what they wrote. Anyone on either side was aware that they were really doing different aspects of the same thing. So this is some measure, perhaps, of isolation. This is just going from what they wrote, as I said. And then we get 1950 to 1970, what Novikov deemed the golden period of topology. This was a period when topology was very much focused on natural questions in the sense of Gromov. Classify all manifolds up to homeomorphism, PL equivalence, or smooth structure. Then, then something happened, and topology started to reintegrate with the rest of the world. I should mention it never fell down to, I mean, there were always some applications going on. This is only a general trend, and you may disagree with it. Novikov gave one plausible, he thinks possible explanation. I will give another for internal topology, but I would urge caution on these explanations. Let me tell an anecdote. I showed this graph to Cliff Gertz, who's one of the leading anthropologists, a colleague of mine at the Institute. And he said that in anthropology, the exact same graph is true with the exact same dates. And he could list all of the things which would go on at these various times. So, of course, we like to tell the history of mathematics like we're this independent thing, not related to the rest of the world, but perhaps we are influenced by some zeitgeist. Anyhow, what are the applications of topology? Well, here are some. Topology has been applied to algebraic geometry, Lie groups, number theory, combinatorics. I'm not going to speak at all about these applications down here or many others, partly because I haven't worked in them myself, and also maybe because they don't fit into my paradigm quite so neatly. Now, if you think about these applications and think about the spaces that are involved, in every case except for the case of compact Lie groups, the spaces involved are singular. They are not manifolds. Now, it's a historical fact, which I'll go into in a minute, that this date, 1970, the date that Novikov gave as the date of the collapse of topology, is the date of the foundation of singularity theory.
That's what he left upon.
Yes. Right. Well, So my alternative explanation of this phenomenon, at least within these fields, look at these early applications. So Cartan was applying topology to the study of compact Lie groups. He looked at their homology theory using de Rhams' theorem. De Rham was his student. Okay, so that was the smooth case. Lefschetz was looking at algebraic geometry, but he was perhaps one of the first people always to put smooth in front as an artificial hypothesis. Algebraic varieties aren't smooth, but Lefschetz decided to study the smooth ones. The generalization of everything he proved to the general case had to wait until after this date. So in some sense, the applications of topology at the beginning were things which could be treated in the smooth case, and many of the applications at the end, I would say, are because we are now able to treat non-smooth spaces on the same basis as smooth ones. Okay, so I'm going to come back and give some sample cases which I've chosen among many possibilities at the end. In earlier talks there have come up some of the applications in algebraic geometry and in group theory, so I'll give some in number theory and combinatorics. Let's make sure we're all talking about...
In the Lie group example, that's singularities when you consider orbits, right?
Right, exactly. And there's this incredible Lustig program, you might say, of solving almost every problem in algebraic group theory by looking at these singular orbits and looking at the intersection homology of the closures of the orbits. Right, so as soon as the group is non-compact, then the closures are singular. Oh, sorry, maybe I should revert to this. Okay, well, a singularity is just a point where it's not a manifold. Not all of these, I should have said, not all of these spaces here are themselves singular, but they're very often non-compact. For example, that happens with this example here, modular varieties. And the compactifications you're forced to use will be themselves stratified or singular. Okay. And another final comment that somehow singular spaces have so much structure that somehow it's very easy to think of invariants for singular spaces. I mean, because every point has a link, which is itself a manifold of smaller dimensions, so you have all of this sort of infinite array of data, or I mean finite in a given case, but potentially infinite. And to put all of that together in a way which will actually apply to something, you have to, in my opinion, have the applications in mind. That is, the study of singular spaces for their own sake. There are people who do it, but this seems to me a little bit dry as a subject. Well, now let me say something about the history of this. Before 1960, in Novikov's golden period, was the Dark Ages. Actually, you can look at various works written then, people who were trying to say something about singular spaces. It sort of illustrates Kleinerman's point that when you try to do something in the wrong era, you won't be able to succeed. I mean, there are some very noble but ultimately failing papers written. Just an indication as to what things were. Bill Fulton told me that when he was a student at Princeton, there was a big debate about whether every point on a complex algebraic set would have a cone-shaped neighborhood. You know, could there be sort of infinitely many things happening as you approach this? So this was a popular subject of discussion. People people were aware of the problem but had no idea as to how it might be solved.
Is there really doubts about that it may be not common? I mean, just
What
That's
category,
in what category?
complex algebraic varieties.
though? No, but cone in what category?
Oh, topological.
Oh.
And people doubted that.
That's what Bill Fulton told me. I wasn't there.
It's hard to believe it, right?
Well, no, I mean, there was an expected answer, but some people thought, well, maybe it wasn't true, and in any case, they thought that you know, it would be very, very hard to prove. Well, anyhow, I'm quoting. I can't defend it since I wasn't.
Phil Martin's thesis at that time was proving some conical property.
I see.
Variety. That was that era exactly.
I see. Okay.
Same time.
Anyhow, there was a huge series of giant steps forward in one decade period. There was Hironaka who found a smooth space which mapped to this. The main point of that is, as we think now, that enables you to sort of study a neighborhood of the singular point by using coordinates on the smooth space. Whitney had various ideas about various tangent structures you can have. These ideas turned out to be just what you needed in order to understand it, but he himself wasn't able to prove that. It was René Thom who proved that. And, well, anyhow, there were huge steps forward, so that at the end of that period, at least topologically, one knew that every singular space was essentially equivalent to this picture here. All the singular spaces that came up in the slide I have a structure which is, perhaps this point is replaced by a manifold and this link is replaced by a bundle, but in any case it's essentially some finite structure like that. And then after that there's been a flowering of many things and applications to all the fields that I was describing at the beginning. Perhaps before leaving this, let me mention a couple of problems. The first problem is, well, we really understand the topology of these spaces, but we don't understand their differential geometry. And by that I mean you would sort of distinguish a space like this from a space like this, because here the sort of rate of growth is different. Well, if that's the only problem that you met, it would be a pretty trivial thing. But in fact, if you look at any reasonable complex algebraic space, you have many different rates of growth, very complicated sets, all contracting at a different rate, all of which the topology completely skips. In some sense, this is why it's very hard to resolve questions about L2 cohomology.
Is there an example of a complex algebraic variety which isn't in Lipschitz category cone-like? No? Yeah.
Yeah, I mean, I think as soon as you look at anything, it's not. But anyhow, maybe we should.
Singularity on a curve is flat,
Well,
so it's cone-like.
yeah, curves are all cone-like. But I think as soon as you go to the very first surface singularities, it's not. But in any case, maybe we should discuss that. I mean, you have these circles in the middle of a thing which are being contracted very fast, whereas the whole thing is not being contracted very fast. So that, I mean, that happens in the very easiest, the very first surface singularities. Anyhow, it seems to me that this is a problem of a very interesting problem to try to invent a structure for this, but it may not be one that mathematics is ready to solve. And also, I don't want to give the impression that singular spaces are the only spaces that come up in applications, which, anyhow, it seems to me that spaces that come up with iterative processes, turbulence dynamics, should have also a topology appropriate to those. There are some naive things you can say, but I would guess that there are things which haven't been, that there's a theory there which so far hasn't been really laid forward. Well, In the remaining time, I want to discuss a couple of examples of the paradigm I've been presenting, where you look at a class of spaces that comes up in nature and look at nature, meaning other fields of mathematics, and look at the problems that come up with there, and then this leads you to develop new topology. So the first example I want to discuss is modular varieties. So these are basically locally symmetric spaces. So this is these are Riemannian manifolds which have a local involution, meaning that if I have a point on my manifold, then there's some neighborhood, so that the map of that neighborhood that I obtain by point P, there's some neighborhood, so that the map on that neighborhood I obtain by taking x to minus x. That is, I extend the geodesic from x to P by the same distance in the opposite direction. That gives me a little involution if the neighborhood is small enough, and I want that to be an isometry. So this is a beautiful property discovered by Cartan. Then I want them to be complete. That means if I take a geodesic, I can keep on going. I don't fall off the edge of the manifold. Then I want them to be finite volume. Since it's a Riemannian manifold, volume makes sense. And finally, I want them to have an arithmeticity problem, which I won't describe, but it was implicitly described in many previous lectures. On the other hand, according to theorems of Margulis, this is automatically true in most cases. So by and large, we're just talking about this class of spaces here. Okay. These spaces are non-compact. They have these, as drawn here, they have these things, these hairs going off the edges. Now,
So something that can be stated just in terms of finite coverings, right? That's Margulis'
Yeah.
theorem.
Right.
So it can be stated without, for a high school student. I don't know what it is, but
What? Margulis?
Margulis. No, never mind.
Yeah, okay, but I want, I have something else,
Okay.
some other direction in mind.
It's a quotient of symmetric space by discrete.
Yes, so essentially this means how pi 1 of this acts on the simply connected covering space as always, and the arithmeticity is how that sits inside the group of all automorphisms of the simply connected covering space. Now, what do we care about? What aspects of these spaces do we care about? We care about their automorphisms, meaning self-maps that preserve all those structures. Well, if you think about it, you can sort of prove to yourself that there would only be finitely many one-to-one self-maps that preserve all those structures, and so we're forced to, if we want a rich theory, we need to take self-correspondences. So we have here our symmetric space, our modular variety, and then we have a correspondence which covers it, so that this source and target covering map are both finite to one and preserve all of the preserve the metric structure. That is, preserve the structure that I'm interested in. So this is called a Hecke correspondence. It differs.
More that there are a lot of those.
Yes, it turns out that there's an enormous supply of these, always.
That's what property 4 means.
Yes.
By Margulis' theorem.
Okay,
That's what I was trying to say.
okay.
I didn't know what it was.
I remember it's by itself, but once we get many functions,
Okay, then so one is interested in the in the action of these things on homology. And well, let's see. The problem that we addressed was to, so I'm talking about joint work with Mark Gresky. This is a series of about 5 papers, of which the last one was just completed last week. It's been going on for 10 years. But the problem is to give a geometric computation of L of C, which is equal to the Lefschetz number of C, trace C upper star, mapping, well, some homology theory, and it's nice if it at least includes intersection homology of a particular compactification to itself.
Is S and T both unramified?
Yes, well, that's what I have in mind. I mean, let's consider the ones way out there, except for finitely many. Okay. Now, here's a comment. There's no. So the idea is to compute this using the Lefschetz fixed point theorem. The Lefschetz fixed point theorem. There can only be a Lefschetz fixed point theorem for compact spaces. So we have to take some compactification in order to compute anything, or else some compactifying mechanism. There's.
What's real complex category?
Sorry?
This category is we don't assume the Hermitian here.
Well, right. In the interest of saving time, I'd like to be a little bit vague. Our theorem is completely general and applies to a certain class of compactifications, but in particular to apply in the Hermitian case, it also applies to the intersection homology of the Bailey-Burrell compactification, which is, from the point of view of the Langlands program, at least what one cares most about, or at least current approaches to the Langlands program, which, as we all know, are blocked somehow. Okay. Now, so you need, anyhow, for any theorem like this, by the way, the reason for this choice is, well, there are several, but one is one would like to compare with the Arthur trace formula. And we've done that. This is, gives the L2, the trace on the L2 cohomology of X itself, which in this particular case is equal to the intersection homology of an appropriately chosen compactification. By the way, the reason why the Zucker conjecture was proved, I mean, the reason why we're able to understand the L2 cohomology and understand its topological invariance is that this phenomenon I was describing before of the differentiable structure near the singularities where different things grow at different rates, well, it happens here, but it happens trivially. There are sort of at most 2 rates, and you know exactly what the exponents are, and so you can write everything out. Whereas for a general algebraic variety, it's much more complicated. Okay. Now, you need, let me make my plug for singular spaces. In order to do such a thing, using a Lefschetz idea, you need a compact space. As many people know, there are many compactifications, and there's the one by Mumford and co-authors, which is smooth. However, the Hecke correspondences never extend to that one. So if you want to embed this picture in a picture where, like this, which you'll need to do in order to prove a theorem of this nature, then you're forced to have singularities on the boundary. So you're forced to consider singular spaces. Well, I'm not going to describe the details of the construction. As I say, it's five long papers. I love the details a lot, but let me at least say say this, that it forced us to prove a new topological Lefschetz fixed point theorem. That is, to actually do the calculations of the components of the fixed points. I mean, we want this to be a sum over fixed points of something which we can actually compute in order to make this work. So in order to get something that you can actually compute, we had to write a new Lefschetz fixed point theorem, which was fun in itself and has found separate applications. So it's an illustration of the general principle that when you, as a topologist, you study spaces and questions that come from other domains, you're led to interesting things. Actually, instead, I'd like to bring up another couple of problems. First of all, what is the complexity of some homology calculation for x or x bar? Actually, this question really doesn't depend so much on whether I've compactified or not. The question is, how can you store in a computer the topology of x in such a way that you can compute its homology? Well, there's quite a bit of technology on this. I mean, we like to think we can compute the homology of everything, but actually in this case, it's not the case. Symmetric spaces roughly divide into two big domains, the linear and the Hermitian, and they intersect in SL2, which, as we learned, is the one that the analytic number theorists like most. Oh dear. No, there's a whole classification, but GLN is linear. Yeah, right. Linear means that basically what it means is that I can put on the symmetric space itself, I can put a linear structure where if I'm given 2 points, I can connect them by a line. Well, maybe that's every space because I can take a geodesic. And then if I'm given 3 points and connect those 3 lines, then if I draw all of the lines like this, I get the same surface as if I drew all of the lines like this. So, and so on, as I go up. And this is obviously a good thing if you want to triangulate a space, because it means if you sprinkle points in there, you can start getting triangles out of the sprinkling of points. Now, I don't claim that there's a theorem that there is no such structure on the ones which don't fall in this class, but nobody's ever found one, and if you did find one, it would solve a very big problem. So, yeah, basically I'm describing a projective structure, but not necessarily. Well, I mean, it doesn't make sense to ask if it's compatible with the metric. Yeah. Okay. Now, because of works of Voronoi, again, in this century, but at the beginning of it, Voronoi, in following his ideas, he was an amazing mathematician who died sort of right in the middle of writing a series of papers on this. You can write a computer algorithm for calculating the homology of all of those. But in fact, you can write, no one even knows how to write a computer algorithm, so these are computable. Well, you can write a computer algorithm, but then there's the matter of the growth of the algorithm. And the algorithm grows so fast that SL3 is the last one that anyone has actually been able to do enough calculations to give an instance of the Langlands program by actually doing this. Now, there are, to my knowledge, only 2 other examples here where you even know of a computer algorithm. One is the Hilbert modular surface, and the other is the Siegel modular threefold. And this was joint work with Mark McConnell, one of the hardest papers I was ever involved in. So for all of the others, even in this in-principle algorithm, it's just unknown. On the other hand, so what does this Voronoi algorithm do? It actually displays the thing as a cell complex. On the other hand, one has the feeling that you're doing something wrong here, because this grows so fast. So perhaps there's something more efficient to do.
Where's the triangular modular space? Is that over there on the right?
It's widely regarded as being analogous to these, and you can say similar things.
But there's an algorithm there.
That's right. There it would, and in fact, if you know that algorithm, the ones over here are really quite similar to that, and even this one, the one we found for that, is really quite similar to that. Anyhow, one has the feeling that you've made a bad computer science judgment by deciding to triangulate this space. On the other hand, triangulation or cell complexes is virtually the only way we know how to present an arbitrary space on a computer. So I have the feeling that there's something missing here. This is definitely relevant to...
Could you estimate how difficult is structure, including standard iterations and so on? Could you look to the answer, not the way of computation, and to see
right.
whether you could expect anything?
Right. This is sort of what I'm suggesting. I mean, when there's a whole community of mathematicians that works on this, and they keep hitting a sort of a glass ceiling here. And when that happens, as we were told in earlier lectures, doing exactly the kind of thing that you're suggesting seems to be a good idea. It seems to me this question is at least relevant to Peter Sarnak's question. What is the reason for the success of these spaces in answering questions in number theory? Because it does appear that these spaces are incredibly complicated. At least the best algorithms we have, in the case where we have any algorithm, is incredibly complicated. Whereas we are able to extract information out of them by various means. For example, we were able to extract this information. I mean, it's not surprising. It's always easier when you take an alternating sum. In fact, that was in Poincaré's original paper. But the answer to this is just far less complex than the answer to that. While I'm at it, because we're supposed to speculate wildly, let me add one of my favorite speculations. Can you consider the action of C as a dynamical system? Basically, I'm suggesting two fields of mathematics which have not yet been brought to bear on modular varieties. I mean, they sit in the middle of all mathematics. They touch almost everything. Well, see, in order to do this, we had to calculate the fixed points of C. So the fixed points...
Only the multiplication.
Yes, but it turns out that the interesting dynamics are on each piece. It's basically hyperbolic near infinity. So yes, on the compactification, but it will be equivalent to doing it on the interior, the same depth. That's true of both of these questions, really. I mean, we understand the singularities. It's the interior that we don't understand.
But in this case, even if you take a compact portion, but still question exists.
Yeah.
So
Both.
The question is not related necessarily to compactification.
Right.
You take a case where the compact portion asks the same question.
Right. Neither of these questions.
What is the question then? Can I repeat the question? Say, how compact?
This one?
As a dynamics.
Well, first of all, you have to make sense of it. So far as I know, people who study dynamical systems have not considered one-to-many maps, but I don't see any reason why you couldn't. Oh, I'm wrong?
John Bullitt has made a beautiful study of
Also Friedland.
Okay.
I mean, it's not a general theory, because there's problems not that they don't satisfy a certain property, which is very important in discrete groups or in the generative.
Anyhow, here's a case where you know in advance that the thing contains some of the deepest information we have in all of mathematics, and yet the set of fixed points are the set of recurrent points you can compute, and they are not so complicated. So maybe there's something interesting going on.
What did you say? You refute what?
You know that these things, C, contain some of the deepest mathematics around, but the computing their fixed points or recurrent or points of finite order is not so complicated. And so, well, anyhow.
So maybe this deepness is in the other part of the
Yeah,
dynamics.
right.
Okay.
Yeah, maybe there's something beautiful going on in dynamics.
But that dynamic is essentially independent, right, on geometry, underlying geometry, pure group theoretic, right?
Yes, this will be extraordinarily non-generic. As a dynamical system, this will be extraordinarily non-generic.
If you change geometry of the space, you have the same dynamics. Pure groups, or am I wrong? Just change geometry.
I don't, actually, I don't know how to change the geometry preserving the whole problem.
You have a compact space, compact.
Yeah?
You change underlying geometry of the manifold.
Oh, yeah, okay.
It has the same dynamic, the same Caesar, and etc.
Uh,
Oh no.
well, I mean,
How much group theoretical, how much is geometric?
I don't know. Well, anyhow, I'm not sure I understand the question.
No. These dynamics, because these maps are localized symmetries, have a certain property. Right?
Yeah, I mean, they're volume preserving, they're
I mean, you can
they're
include
isometries.
geometry into statements about the dynamics.
In my remaining 2 minutes, I'd like to just say a couple of words about another problem, sort of as an excuse for some philosophical comments. As you may, well, as has come up also, this is from combinatorics. Polytopes lead to algebraic varieties. By a construction, you take my version, you take the polytope, you take the cone over the polytope in one higher dimensional space, and then, so that gives you a cone. Oh, I should say rational polytopes. So,
What is a rational polytope?
let's just make the integrals the vertices lattice points after some scaling.
They're convex sets?
Yeah. Convex hull of a finite number of lattice points. Well, maybe I won't say much about this except to say that this toric variety is pieced together out of a bunch of tori, one for each face of the polytope, and the angles of the faces of the polytope give how to glue those tori to each other. So I don't think anything I could say in 2 minutes would add to this. But I do want to make a philosophical comment. The idea that there should be strong interaction between topology and combinatorics goes back at least to Whitney, who was a founder of both fields. He certainly felt that there should be an interaction, but the example that he had was mainly simplicial complexes, which is a very inefficient way of building complicated topology from a combinatorial set. This toric variety construction, instead of sort of putting together simplices, puts together tori, and that's a little more efficient. So you can build a fairly complicated space out of a fairly simple polytope, and that's somehow why it's useful, I would say. And that may also illustrate what I have in mind with this question here. The only things that we've been able to do so far are to try to build these spaces out of contractible pieces, but maybe there's some more clever thing that we just haven't been able to conceive of, which will help.
You want out of this singular space produce some algebraic geometric concept, yeah? What? Yes.
No, wait. An algebraic geometric object you have. This is
No,
this.
there may be another object. Yeah, more subtle.
Something that allows you to compute the homology. Something that you can write an algorithm to compute the homology. That's what I ask. Okay. Well, so we had a very pleasant experience, Tom Braden and I worked on a conjecture of Gill-Colli. There was some noise during Gill's talk that perhaps he shouldn't be calling his things conjectures, but let me tell you that we got a lot of fun out of one of those conjectures. It turned out to be to lead to very interesting new topology. Well, I'll state the conjecture, but perhaps not the proof. You see, this is a singular space, and so we can say G of the polytope is equal to the intersection Poincare polynomial of this toric space, the space that I've calculated there. That space is contractible, by the way. Somehow it all contracts down to a point, but intersection homology is not a homotopy invariant, so it still has very interesting intersection homology groups. Gill's conjecture was that G of P, this turns out to, I should say, I won't give the algorithm, but this turns out to depend only on the combinatorics of the space, how the spaces, how the various spaces fit to each other. So there's a relation one can give. There are many ways to give it, and the fact that this is positive is one of the strongest statements we have about the possible combinatorics of polytopes. Of course, we have it only where the toric variety exists, so only for rational polytopes, which, by the way,
Definition?
yes. But this doesn't show that it's a combinatorial invariant. Anyhow, Gill's conjecture was that G of P is bounded from below by G of any face times G of P divided by that face. You see, if I take a face of this thing after making it a cone and sight along a ray, then what I'll have left will be another cone. And so that's what this is. And greater than or equal means every power of t, the coefficient here, is bigger than the product there.
For a triangle, if f is an edge, what is p mod f?
For a triangle, if f is an edge, p mod f is a line segment, and therefore p is a point. Triangle. Well, I mean,
What's the operation of convex sets? If you have a face,
take a nearby plane that sort of slices the thing off. If you have if this is f, then p mod f would be that thing.
I mean, what part of the figure is p mod f? Sorry.
This, the sort of the link. Okay, so this is this gives, I mean, it hasn't been explored, but gives some quadratic statements about possible numbers of edges and faces. And as in the case of the Lefschetz thing, it led to very interesting unknown statement in topology that was a lot of fun to play with. Okay, well, let me stop. Perhaps if I'm to make a moral, let me state it this way. I mean, in some sense, maybe what I'm doing is appealing for the unity of mathematics. People should look at problems that come from other fields. But really, I don't want to do that because I don't like it when people say other mathematicians should do something for the good of mathematics. I think mathematics is best served when everybody goes out and does their what appeals to them most. unlike the National Science Foundation that tries to push us to do otherwise. But maybe I should put the moral this way. If you're a mathematician and you want to work on a problem which will continue to be fun and which will avoid the twin dangers of Gromov, which are basically dangers which mean that you'll start to work on a problem and spend a lot of time, and then it'll turn out that it won't lead anywhere, and you'll be left with an unfun toy. If you want to avoid that, then a good thing is to work on problems that have already been tested in some other subject and are known to be deep. Okay, thank you.
Questions? Is it processing?
Yes, that's what Braden and I proved for rational polytopes. And then for the others, there's a big unknown with various ideas floating around.
Is there a definition for algebra?
Sorry?
Is there a definition for algebra?
Many, many. Yes, many definitions. Maxime has one. There are others. But
This definition uses rationality because you get variety.
right.
What
But, well, I didn't give it.
what definition are they asking about?
Something which would be the intersection homology of an irrational polytope if you gave an irrational polytope. And yes, there are a number of complexes that you can write down which do calculate to which the integrality of the vertices has no bearing at all, and which do calculate this group if the vertices are integral and make sense otherwise. And so one can and does make the same conjecture about all polytopes, but it's unproved.
So I have another question. So in this Lefschetz trace form of Hakea correspondence, have you ever encountered some kind of Lefschetz trace form of Hakea correspondences which are not finite over?
What do you have a? Perhaps you could show me an example.
Well, I mean, what you give in mind is not exactly Hakea correspondence, but something analogous to that. But, okay.
Right. So.
What was the question?
So according, the question concerned things which are like Hecke correspondences, but in which the maps S and T are not finite. And so immediately my principle is that one shouldn't take this as an abstract question, but one should look at the example. So I would like very much to see to see your example.
You mentioned that this computation relates to the Langlands conjecture. You mentioned Langlands at the beginning of the lecture.
Yeah.
And so can you say exactly what you...
Well, I'm not, how many lectures are going to explain the Langlands conjecture? No, the Langlands conjecture says that, I mean, these C's in general are parameterized by things like primes, and the Langlands conjecture says that the action, well, this number, or the action of this, as you vary over the different primes, should contain number theoretic information about those primes. So perhaps there should be an algebraic variety that it counts the points on, or perhaps something like this.
So this computation can be made to support it.
Sorry?
So in your computation, you should make supports in some examples. You can compute the traces for overall primes.
Yes, yes, you can compute them. You give a long formula, and then there's a whole program sketched out by Langlands and his students.
But in this particular case, you compute it.
Yes.
How it bears with respect to general conjectures.
Well,
You said it confirms it.
it's
Exactly.
no. I don't say it confirms it. Then that fits into a long program which Langlands and his students are pursuing, which has as the goal to actually prove the Langlands conjecture, and so you have another long formula coming from the.
We know that, but just you said that what you computed.
Yes.
You said
No. He made a very clear statement about the Langlands conjecture that was perfectly understandable to me, and I don't know what the Langlands conjecture was. He just said that the compactification that he needed to make this theorem true, in some cases, was the one they want to use in their attempt to prove the Langlands conjecture.
This is what you said.
That's just what he said. So whatever Langlands conjecture is, you're not going to know what it is.
No, but this is not the statement. It's not a computation. Some computation.
Did he also, that's the only time he used it.
No, this is only a step in a. No, I mean the Langlands conjecture doesn't have the structure that you can usually take the answer and say, ah, yes, that corresponds to arithmetic.
This is what you meant when you referred to language condition. This was my question. I still don't understand. Okay, so we resume in 10 minutes.